Hello everyone, I'm Shivam Gautam, and today I'm going to present our work SDVTracker, a recurrent model for real-time multi-sensor association and tracking that is applicable in the autonomous driving domain. This work has been done in collaboration with Greg, Carlos, and Brian during our time at Uber ATG. To begin with, let's take a look at how classical object tracking systems work. An object tracker takes in detections as an input from an upstream object detector. These detections are then passed on to the associator, which tries to associate each new detection at time t to previously existing objects at time t-1. This is usually done by creating pairwise scores using distance metrics such as IOU or L2 distance, and then performing either greedy or Hungarian assignment. Post-association, these detections are used to update the state of the matched objects using filtering-based methods like the EKF or the UKF. These updated objects are then passed downstream onto trajectory prediction and motion planning modules. Such tracking systems require the association and state estimation to be robust in diverse scenarios. Any errors in association could lead to breaking the single source assumption in the EKF or the UKF filters. Missed associations also lead to spawning more false positives and false negatives. Poor state estimates, on the other hand, lead to cascading errors to downstream pipelines, further degrading system performance. Let's take a look at some challenges in developing a robust tracker on a typical urban scene. Here is a portion of the scene which is difficult to pass even from the naked eye due to there being a high density of actors in an area. Even with both the camera and LiDAR input, it is difficult to identify the number of actors within the red box. There are 2 pedestrians and 1 bike in this dense cluster. Anytime we have detections this close to each other, the task of association and state estimation becomes even more difficult. Another challenge is that each of these actors often receive multiple detections from a 2D camera detector and a 3D LiDAR detector that need to be fused to an existing track. Each modality has different error characteristics. For example, range estimates from camera detections are generally more noisy as compared to LiDAR-based detections. This makes associating multimodal detections to an existing track very challenging. Trying to associate and track actors as they go through occlusions is another failure mode. Both the 2D and the 3D detections for the objects in red are only partially visible. Hence, we need a tracker that is more robust to such occlusions by being temporally consistent through occlusions. Finally, it is difficult to accurately track the motion of different classes of actors. As we can see, we need to track pedestrians, bikes, and even skateboarders, each with its unique motion model. Coming up with a single motion model with parameters that can accurately fit all classes is extremely difficult. So we need a tracker that can track all classes with different appearance and motions jointly. Hence, to overcome these challenges, we propose SDVTracker. It is a learned method that uses a sequence of object detections and an LSTM network to jointly predict both association and tracking for an actor. This allows our method to learn a nonlinear association that scales better as object density increases and persisting appearance through occlusions. It is a real-time method designed for operations on an SDV and runs within a strict timing budget. Unlike previous methods that employ expensive feature extraction and deeper networks, we show that a single LSTM cell with the right feature set can beat classical techniques for tracking. It is multi-sensor, taking in both LiDAR and camera detections to associate to tracked objects. Compared to classical methods, our method scales better when trying to incorporate multiple sensors. Finally, our model learns the problem of association tracking jointly by using the same model for all actor classes. This allows for robust association during occlusions and when varying motion models of actors is an issue. Here is what our system looks like. We take in an input detection from time t and passed objects from time t-1. We perform joint association and state estimation to get learned associations and a learned tracking estimate for each potential association. We use these inside an interacting multiple model or IMM filter, which is a combination of multiple EKFs and the learned state estimate. After the state update from the IMM, we finally get the updated set of objects at time t. Here is what the model looks like. We have an object detection pair as an input to the model. We perform feature extraction from the object and the detection to extract relevant motion, shape, and difference features. We pass these features to our learned model and jointly predict targets for both association and state estimation. For association, we predict an association probability and an association score. The association probability is set to 1 for object detection pairs that overlap with the same label, above a certain threshold. We also regress the score for this object detection pair, which is based on the distance between the label centroid and the centroid of the objects and the detection. For learning the state estimate, we regress the x and y position of the object along with its velocity. We also regress the corresponding uncertainty for each state variable. Next, we move on to our experimental setup. We use the ATG4D dataset for evaluating our model, since it is sufficiently large enough to validate our scalability. We use pre-existing metrics from the 2D tracking domain like MOTA, MOTP, etc. We also propose a new set of metrics, MOTVO, designed to measure velocity outliers, and MOTVE, designed to measure velocity error of 3D tracking systems explicitly. These are required as they measure quantities that downstream systems like trajectory predictors rely on as a prior. We compare a learned method to previous methods that use IAU, L2, and Mahalanobis distance-based association. We show our results on both a LiDAR-only and a LiDAR plus camera system. As we can see, we see significant improvements in tracking metrics such as MOTA, FP, ID switches, MTML, and fragmentations. We also see a significant improvement on our proposed set of metrics, MOTVO and MOTVE. One interesting result to note is that even though one of the classical methods performs well on the MOTP metric, which is a measure of the error in the position of an object, that does not necessarily translate to improvements in velocity, which is much more important for self-driving vehicles to accurately predict trajectories. Next, we show how these methods cope with the multiple types of detections, both from LiDAR and camera. Here, the true limitations of classical methods come to the forefront, as we see significant regressions in other methods when asked to associate cross-modality. We further performed ablations to understand the impact of our novel joint regression, the recurrent network, and using the IMM. While using an LSTM and jointly regressing state are clearly better, adding the IMM on top of our LSTM state estimates marginally improves performance. We then demonstrate the effectiveness of our method during crowded scenes, since that is when association is most challenging. We show that as crowd density increases, our method significantly improves over the next best method. For a scene with 100 pedestrians, our learned model reduces poor velocity estimates by 45%. We further show that our method runs within a strict timing budget and scales well with the number of actors in the scene. Now let's take a look at the model in action. On the left, you can see one of our baseline methods trying to associate in a crowded scene, and frequently showing bad velocities due to misassociations. On the other hand, our method is more robust to such scenes and can accurately associate and track in such complex environments. This concludes our presentation. Thank you, and feel free to reach out in case you have any questions.